Good morning, everyone. I'm Brock. So today, let's keep working on a lit quiz question. So, okay, this is a medium question. So let's have a look at it. The question is minimum number of work sessions to finish the tasks. There are n tasks assigned to you. The task tab are represented as an integer array tasks of length n. Whether the f task takes task n hours to finish. A work session is where you work for at most session time consecutively hours and take a break. You should finish the given tasks in a way that satisfies the following conditions. If you start a task in a work session, you must complete it in the same work session. You can start a new task immediately after finishing the previous one. You may complete the tasks in any order. Given tasks and the session time, return the minimum number of work sessions needed to finish all the tasks allowing the conditions above. The tasks are generated such that session time is greater than or equal to the maximum element in task I. Example 1. So the input tasks is 1, 2, 3. Okay. Which means that we get all 3 tasks, right? And the time it takes is 1 hour, 2 hours, 3 hours. Session time is that you must have a break every 3 hours, or you work at most 3 hours. Okay. So, first work session, you can finish the first and the second task. Second work session, finish the third task. So the output is 2, right? You need 2 work session. Example 2, you get 5 tasks, 3, 1, 3, 1, 1. Session time is 8. So in first work session, you can finish all the tasks except the first one. In the second work session, you can finish the last task. So the output is 2. The third example, you get 5 tasks. 1, 2, 3, 4, 5. You get session time is 15. You can finish all the tasks in one work session. So the output is 1. Okay, I think that I understand what we want to do. So again, let's pause a little bit and think about what we can do here. So yeah, so n is smaller than 15. So actually it's pretty small, huh? We can represent any subset of tasks as a Bitmask and pre-compute which subset can fit into one session. Right? So some observation. we can represent any subset of a task. Tasks as a Bitmask. And a precompute, which tasks can fit into one session, one work session, right? Because what we need to do is that we need to fully utilize a session time as much as possible, right? You don't want to have any waste. Then maybe we can calculate the minimum sessions to finish tasks in the mask. Right? We need to calculate the minimum sessions to finish all tasks. In the Bitmask. And how to calculate that? So we can try all submasks that fit in a single session. So let's say make this one, let's say as DP mask. And then this is minimum. and return. So maybe let's think about the test case. So let's say we make task is 3, 3, 3, 3, 3, right? And make session time as 3 as well. So in this case, every single task require a full session. So the first step, so the first step we need to check we need to check each how many tasks can fit into one single session, right? This is what we need to do. Then we find no two tasks can fit into the same session. And the second step we need to do each task needs its own session. Then we return 5. So firstly, let's get the task's length, right? And let's do a Bitmask. And this operation is to do a bit shift. Right? Imagine there is 1, which is 0001. And then now we left move it to n bits, and we get, something like this, right? Then we need to initialize it, right? Each submask. So initialize the array of for each subsite mask. And then let's build loop. We need to iterate over all subset masks. So which is 4 masks in range So let's, this one is total time for tasks in this subset. Okay. Make a copy of the mask. I is index for tasks, right? We have mask to iterate subset of masks. We have I to iterate tasks. And then what do we need to do? We need to loop where there are side bits in M. Why? Because we want to ensure that in the masks, we can find the array. So we loop the mask. And we need to check if the lowest bit is site. So right, the lowest bit, when M and 1 is equal to 1, is true, then it means its lowest is 1, right? If that happens, what we need to do? It means with that way we will add the tasks. But what if the sum already exceeds session time? So if sum already exceeds session time, then what do we need to do? We need to break it, right? And we can right shift M by 1. To do what? To check next bit. Make sense? And then we need to move to next task index. Okay? Else, so the whole loop completed without break. Without break, what does that mean? It means as it's smaller than session time, right? If that is the situation, we will say this mask is true, correct? So basically we mark this session as valid for one session, right? Okay. So now we need to calculate the upper bound sent here, bigger than possible session, right? Set a upper bound. Because at most, it's impossible to bigger than n, correct? Then we can initialize upper bound. Right? So if it's zero, then if there's zero task, then it requires zero session. Make sense? And we check each non-empty mask. So what we to do is check mask in the range. So we start the full mask as a start point, right? Then what do we need to do? We need to iterate through all submasks of the mask. So And we need to check if this submask is in one session, right? So within one session, then what do we need to do? Then we need to consider doing sub as one session. Make sense? So then we updated the DP mask. And then move on to the next mask. Then we should return the minimum session for tasks. Let's try first. try to run it first. I assume there should be some, well, bugs. Okay. I think this one is a little bit complex, and let's again, please explain the building functions and the methods I'm using, and step by step test the case in the worst case, right? So I think that the core idea is that we utilize a Bitmask to check each subsite. That's a key idea we are using. And the most tricky part is how to use the Bitmask, because they are actually two levels, right? The first level is a subset of the mask. The second level is each element in that subset. So that's two levels we need to check about. Okay, so here are some building methods or functions we're using. Len task, number of task. Range, mask is to iterate integers 0, 1 to max mask -1. List operation, like false multiply max mask, will quickly allocate arrays. Bit shift. So this is to make one is 001, right? It's left shift n bits. It's a count of all subsets. I think that, okay. I think this is something is very tricky. So can you explain? Visualize the way, right? I think that for some, ideas is pretty abstract, and maybe we need a visualized way to understand it. So, how to pronounce it? So, one left shift bit shift left shift n means take the binary number n and shift it left by n bits, right? And mathematically, is actually it's equal to 2 square n, right? Because previously it's 0, 0, 0, 1. Now it become, let's say, 1, 0, right? Or 1, 0, 0. For example, if n is to 0, then it's still 0, 0, 0, 1, nothing change. If n is 2, if n is 1, then it become 1, 0. And if it's if we have one task, then there will be 2 subsets, right? So the maximum task will be 2. And if n is equal to 3, then what we get is 1, 0, 0, 0. Right? Because it's left shift 3 times. So, and then we will get 8 different situation, right? This is just the n square, how do you say that? The power, n power to 2, right? So 8 situation, and so on and so forth. So to summary, the total number of a subset of n task will be 2 the power 2 to n. How to pronounce? 2 to the n. 2 to the power of n. Okay. Yeah. So the total number of the subset of n tasks will be 2 to the power of n. And a way to loop through all masks from 0 to how to pronounce this one? Yeah, 1 left shift n. Okay. Yeah. So the total number of subsets of n tasks is 2 to the power of n, or 2 to n. A way to loop through all masks from 0 to 1 left shift n minus 1. This will cover every subset. Let's go back. So yeah, so this is what we mentioned just now. And the bitwise AND, m and 1 will test the lowest bit of m. Make sense? Because we just use the rightmost bit. And the right shift m, right shift 1. Right? Let me see how to pronounce this one. M right shift equals 1. Okay. And actually this is M equals to M right shift 1. I guess that, a little bit confusing is that how to remember, let's say M right shift 1 and M left shift 1. So you see, M right shift 1, the bit will move right. So 1 will, so in this situation, it will do right shift, bits go right. It's actually divided by 2. And bits move left. It's left shift. Then bits will multiply by 2. So the arrows actually tell you the direction. Right? Right is reduced, left is larger. And the direction is the direction is okay, left shift. So I guess that it's like how do you say that? It's just like
funnel,
funnel. It's like a funnel, right? So for the left shift symbol, you can imagine on the right side, this is the input of a funnel. And on the left side, it's the output of the funnel. So which means it's left shift. And for right shift, right, you can imagine the input of funnel is on the left and the output of the funnel on the right. So which means it's right shift. Okay? Okay, let's go back. I always think that question related to bit operation is pretty tricky. Bitwise all is mask. Okay, how to pronounce all? X all. Okay. So bitwise X all. This will remove bits of sub from mask. That makes sense, right? Because you will check whether these two elements is different. Right? If this is 1, and the sum is, let's say, 1, and the mask is 0, then because they are different, then I will get 1. Right? So this is to check whether a task already scheduled or not. And the submask iteration trick. So sub equals to sub minus 1, and the mask will enumerate all submask or mask excluding 0 without duplication. So you can imagine mask is it's 0, right? So it will I think this needs more clarification. Okay, so let's say mask is this, and we want to visit all subsets where everyone in the mask is also one in the mask. Then submask of this one. Is these options. So there are 8 submasks because we have 3 ones, right? Then the trick here, so we can give an example. So the mask is 10110, and we start it from itself. Then iteration, well, -1 first. So sub is 10110, then sub -1 will be 10101, right? Because literally speaking, it will just go down, reduce 1. And when we do sub -1 and mask, which is the mask, remember, the mask is here. So the last element, so only it will become 10100, which means that the first element and the third element is equal. Then it will clear the last set bit and fills lower bits with ones. And then end with mask filters invalid bits, right? So it will filter anything that doesn't exist. And a similar strategy. So we use this one. Then we get we use this subset -1, and then we get 1010 step down. So basically it keeps step down. When it's 0, then loop ends. So this trick is to, visit every submask of 10110 in descending order. So imagine mask as a bit filter that decides which position can be on. When we do subtracts 1, it moves to the next smaller binary pattern. And with mask, we'll turn off any bits that weren't allowed in the original mask. So it sounds like step down 1 number, then erase illegal bits. This will guarantee every valid submask is visited. Once you skip invalid pattern, you never visit duplicates. I think that this visual analog is pretty straightforward. Okay, again, let's go back to our previous parts. Yeah, so this one we already explained just now. And where else? Patterns else runs only, if loop didn't break. Okay. Yeah, I think that that's some very, tricky building, operations. And let's look at one example. Yeah. So the input is 5 tasks, 3, 3, 3, 3. Session time is 3, right? Our observation is that no two tasks can share a session because any pair sum is larger than 3. So each value subset can have at most 1 bit session. Excuse me. So firstly, we need to pre-compute the valid mask. So valid 0 is true. For any mask with exactly 1 bit set, like 0, 1, 0, 0, 0, 0, 1, or 0, 0, 0, 1, 0, so on and so forth, sum is 3. So it's valid and true. For any masks with 2-bit size, the running sum will hit 6. Then it break, so valid is false. So only valid 0 and the valid I, left shift I, 1 left shift I are true. Make sense? This is in the scenario. And when we try to generalize it, so the base is DP 0, 0, 0, 0, 0 is 0, right? And the masks with 1 bit, which is 1 task. So the original mask will be 0, 0, 0, 0, 1. The submask is 0, 0, 0, 1. Then it's valid. And then DP 0, 0, 0, 1 will be 1. Which means that it's valid. And then we find, all these DPs are 1. Then we count sum them together, which means it's true. That it will be 5. And when we get masks with 2 bits, so the mask become 0, 0, 0, 1, 1. Then its non-empty submasks will be 0, 0, 1, 1, 0, 0, 1, 0, and 0, 0, 1. And 0, 0, 0, 1, 1 will be false because the sum is overlap. It's skip. And 0, 0, 0, 1, 0 is true. And any 2-bit mask will get 2. Then any singleton yields 3. And any mask with 4 bits is 4. And the full masks with 5 bits is 5. Then the answer is 5 session. This is worse the case because number of sessions. Each task must stand alone. But if you want to see some non-trivial packing, more balancing during DP, let's say 1, 2, 3, 3, then valid one session subset. Any subset whose sum is smaller than 3. DP will pick 3, 3, right? And also we can define it's called dynamic programming. But the basic idea is that to store answers to smallest problems, so you don't have to recompute them, right? So basically DP is a table that remembers results. And in this situation, DPmask basically is minimum number of sessions needed to finish all tasks represented by mask. Okay, let's visualize it. If we get 3 tasks here, the max mask will be 1 left shift 3, then it's 8, right? And the masks will iterate from 0 to 7, right? So it means that mask 0 means no tasks. Mask 1 means only task 0. Mask 2 means only task 1, so on and so forth. So DPmask stores the best answer, which is a minimum session, for the particular compilation of finished tasks. So the logic is, if I already know the best answer for smaller problems, I can compile them into get the answer for big problem. So in this situation, this is how we calculate this. And to make it clarified means, firstly, we will take any valid sub of masks that can fit into one session, which is this part, right? Take any valid sub of masks that can fit into one session. And this part means if I already know how many sessions I need for the remaining tasks. And then plus 1 is the total will be that number plus 1 for the next new session. And the last operation is keep the minimum of all possibility. Right? So if we don't use dynamic programming, we need to recalculate the same subsets many times. But with dynamic programming, we only need to compute once per mask and reuse the results. So which means that it will keep, it's kind of like caching, right? So we start from DP00, this change to DPTB001, then DP011. At the end, we get DP111. So I already solved these tasks. I just look up the answer instead of recalculation. And yeah, here's an example. So let's say we have 2 tasks, 1, 2, and session time 3. So when mask is 0, the subside is empty first, right? Can this fit in one session? Yes. So DP mask will be 1. And then we move on to mask 1. The subset is 1. It can, yes again. DP mask is 1. Mask 2 still can fit into one session. DP mask is 1. Mask 3, which means that we have 2 bits, right? Then still can fit in. So DP mask is still 1. Now the final answer is 1, meaning all tasks can be finished in one session. Okay. So DP table means memory of smallest subproblems. Transition rule, how to build big answers from smaller ones. And base case, smallest problem, no directing. Let's say DP0, right? And the final answer is to calculate the full problem. Okay, dynamic program don't process twice. Okay, so again, let's go back. I guess that my source is always, junk and back and forth. Okay, already talk about these parts. Okay, yeah, okay. Yeah, I think that's pretty much of this problem. To summary, in this problem, actually we use a lot, two tricks. We are two main tricks here. The first one is about bit operation, right? Left move. So left move, right move, left shift, right shift, so that we can utilize the bit mask. The second trick is about dynamic programming, so that we don't, we need to use something like recaching. Yeah, that's pretty much it. Thank you, everyone. Bye.